Hi there, and welcome to Unit 6, Lecture 1. So, in this unit, we're talking about the age of the Earth, talking about how to sort of compare different rocks and figure out which rock is older, or in some cases, the specific age of certain rocks. Because, we kind of have a general idea of how old Earth is, but it's important to understand how scientists arrive at decisions around other specific parts of the Earth. So, that's what this unit's about. We're also going to learn some ways to think about the age of the Earth relative to our time on the Earth in this unit, and do some comparisons with that. So it should be interesting, and let's get started. So we're going to start with a pretty long word here. Uniformitarianism is a principle that geologic processes that occurred in the past can be explained by current geologic processes. So essentially, geologists estimate that the Earth is about 4.6 billion years old, an idea that was first proposed by James Hutton in the 18th century. So this guy James Hutton was kind of known as the godfather, or the original father of modern geology. Pretty important guy. He theorized that the same forces that change Earth's surfaces now, like volcanism and erosion, are the same forces that were at work in the past. So, really, he's saying that none of these processes have changed, right? So something like the Grand Canyon, right? Something like a big canyon has sort of come, over time, right? Is evolved over time, and there because the processes that we see with, like we saw in our stream table, have always been happening, right? For the entire 4.6 billion years of the Earth's existence, right? So it's a slow build-up in his estimation, which is pretty contrary to a lot of other people's thinking at the time. So think about this idea, right, and what this might mean for the bigger picture. So Hutton's ideas raised serious questions about the Earth's age, because until that time, most scientists thought the Earth was only about 6,000 years old. So remember, there wasn't much scientific dating in terms of chemical analysis of rocks, right? We had a lot of people relying on biblical interpretations of the Earth's age. We had some basic comparisons of different rocks, but really not much else. So what they really thought was that all the Earth's features, right, geologic features, so mountains, canyons, land masses, all that, formed at the same time. So what Hutton really came along and said is he pointed out that although the past and present processes are the same, the rates of various processes may have varied over time. So in his thinking, there may be rapid periods of erosion, rapid periods of volcanism, rapid periods of land creation or land degradation, but sometimes it's slower, right? So he thinks that that's how you explain some of the irregularities you see across the world. So this was really going against what people thought at the time, right? So again, people thought at the time that the Earth was only 6,000 years old. 4.6 billion was nowhere near on the table, but he was a bit of a revolutionary in that sense. So here's a look at Mr. Hutton himself here, and here's a look at the Grand Canyon, right? So he would have said that this canyon was not put here, maybe when the Earth was created, right? So this did not originate whether 6,000 years ago or 4.6 billion years ago, but this, evolved through weathering. I keep saying the word evolved. Certainly it's not an evolution, but I think you know what I mean. It's changed over time due to the processes of erosion and weathering. So another term we really need to understand, probably one of the more important ones here, is this idea of relative age. Okay, the age of an object in relation to other ages of other objects. So, you and I, if you are a student, I'm a teacher, you are younger relative to me, right? I am older relative to you. And when we take different rocks and compare their ages, we want to say which one is older than the other. That's one way of dating rocks, right? So, for example, if you have two cars. One was built in 2006 and one was built in 2016. You would look at those cars, and those cars would have changed over those 10 years of difference in certain ways, right? The paint might be a little bit more worn, you might have more scratches, more dents, the tires might be more worn down. So we can kind of compare those two rocks just on those appearances, but there's a few other things we're going to kind of take that logic and apply to as well. So one way to learn about the Earth's past is to determine the order in which the rock layers and other rock structures formed. Okay, so let's step back and think about these rock layers, which we're going to call strata. So strata are rock layers. Okay, so what the strata do is they show the sequence of events that took place in the past. So if we take these layers of rock and kind of compare their ages and kind of see what's happened to the rock as time has gone on. Okay, so scientists can determine the order in which rock layers formed by using a few basic principles. Once they know the order, a relative age can be determined for each layer. Relative age indicates that one layer is older or younger than another layer, but does not indicate the rock's age in years. So we're not getting specific with relative dating, okay? This idea of relative age does not tell me that a rock is, 427 million years old. It doesn't get that specific. All it can tell me is compared to another rock, which is older, which is younger. So to determine the relative age of rocks, scientists commonly study layers in sedimentary rocks. Okay, so sedimentary rocks are perfect for this because think about they kind of form these layers over time, right? Think about like a riverbed or something. Compare that again to igneous rock. Igneous rock doesn't kind of form in layers so neatly, so evenly. We'll get into that a little bit later in the lecture. So take a look at some strata here. We're going to get into what these words mean soon, but you can kind of see the layers here, right? You can kind of think about them kind of being stacked upon one another, okay? When you're doing your laundry, you've got a laundry basket, right? There's a laundry basket. The clothes here at the laundry basket on the bottom, really stinky, really nasty. Were put there, before the clothes here, right? And before the clothes here, right? So as you kind of go down toward the bottom, they're older. They've been there longer. They're real nasty at that point, right? Same thing with these rock layers in many cases, right? The rocks that are at the bottom tend to be a little older than the rocks on top. Okay, so here you can see that these rock layers are not so even always just horizontal, not always like that. You can see some different angles, some diagonal ones, and this is a really nice overhead view of a canyon showing these layers of strata. Okay, so the first law, the first kind of rule we're going to talk about when we're trying to figure out rocks relative in age is this law of superposition. It's the law that a sedimentary rock layer is older than the layers above it and younger than the layers below it if the layers are not disturbed, okay, or undeformed, okay? So, and not disturbed means the same as undeformed. So deformation, remember? So if the rock layers are left alone, here's the rule, right? I'll say it again. A rock layer is older than the layers above it and younger than the layers below it, okay? So think about your laundry basket. The older laundry's on the bottom, the more recently placed laundry's on the top. Same idea. Scientists commonly study the layers in sedimentary rock to determine the relative age of rocks. Sedimentary rocks form when new sediments are deposited on top of old layers of sediment. That's just how they form. You know that from our last unit. As the sediments accumulate, they harden into layers called beds. The boundary between the two beds is called a bedding plane. So, if you've got your layers of rock, okay, that boundary, which I'm going to highlight in a different color, I'll use red. Right there, that boundary between the two layers is that bedding plane. Okay. So here's just an example here. This is what we talked about when we talked about organic sedimentary rock and limestone. So skeletons and shells of dead marine organisms settle to the bottom. So they fall to the bottom and start to pile up here. Okay. The layers of sediment are buried under by other sediments. Okay, then the sediments harden to form limestone. So there's soil that falls down above it, right? And we could say in this case, remember using that law of superposition, which is the oldest layer here. That would be layer A, right? So A is the oldest. How do we know that? Well, B must be younger because it layered on top of that, right? And then, so B is the second oldest. C is the third oldest. And D is the fourth oldest, or the youngest, essentially. Okay? So this tells you the law of superposition. All right, so if it's lower, it's older. So here's another idea. Scientists know that sedimentary rock generally forms in horizontal layers. Okay, so from east to west, left to right. The principle of original horizontality states that sedimentary rock layers left undisturbed will remain horizontal layers. So, scientists can assume that sedimentary rock layers are not horizontal. That sedimentary rock layers that they're not horizontal must have been lifted or deformed by crustal movements that happened after the layers formed. Okay, so they're going to assume that they're horizontal. If a rock layer forms like that, right, or some kind of bulge forms up in there, right, you can assume that rock layer that kind of went up there must have happened after, okay, because they're normally horizontal. Okay, another rule here is this idea of unconformity, which is a break in the geologic record created when rock layers are eroded or when sediment is not deposited for a long period of time. All right, so there's three ideas here. So movements of the Earth's crust can lift up rock layers that were buried and expose them to erosion. So think about your layers here, right? If there's a plate movement, all of a sudden we maybe have a fault, and then we have a section of that rock come up a little bit sooner. It gets exposed to the rain, gets exposed to the sun, and starts to erode. If new sediments are deposited, new rock layers form in place of the eroded layers. The missing layers create a break in the geologic record called unconformity. So it's kind of like they're breaking their rules, or not conforming. Okay, so this is sort of breaking this idea of original horizontality, right? That they're supposed to be in these horizontal layers. Sometimes these rules get broken. Okay, there's a few different situations here. A nonconformity is an unconformity in which stratified rock rests on top of unstratified rock. Okay, so it's where we have strata lines resting on top of some unstratified rock. All right, so it's almost like a rounder section below these stratified rocks. An angular unconformity is the boundary between a set of tilted layers and a set of horizontal layers. So that's where we saw before, where we have horizontal layers and above some diagonal or angular layers. A disconformity is the boundary between horizontal layers of old rock and younger overlaying layers that are deposited on an eroded surface. Let's take a look at these. So there's the nonconformity. Okay, so there's the non-horizontal rock, right? So you have horizontal layers on top of the non-horizontal. Here we have the tilted or angular rock, all right, with horizontal layers on top. That's the angular nonconformity. And the disconformity is where we have, so we've got horizontal rock, non-horizontal, and horizontal again. So it's kind of like a sandwich between horizontal rock. Okay, another really important idea to remember, we're going to see this very soon, is the cross-cutting relationship. So the law of cross-cutting relationships, the principle that a fault or a body of rock is younger than any other body of rock that it cuts through. Okay, so a fault, a reminder, is a break or a crack in the Earth's crust, along which rocks shift their position. An intrusion is a mass of igneous rock that forms when magma is injected to the rock. So a lot of you did your Mr. Rock projects where magma built up, right, then eventually moved up and burst out of the surface. That's what we call an intrusion, okay? So if you've got some land here, got your layers of rock, all of a sudden magma, let's make it red. All of a sudden magma bubbles up, right? Right, and if it cuts through those layers of rock, it's intruding. Now, according to this law, that intruding magma or that fault, right, that might break in the rock, there's the fault, those two things are younger than those layers. That just makes sense, right? The layers have to be there first, then you get the breaking. In these cases, scientists use the law of cross-cutting relationships or the fact that a fault or an intrusion is always younger than the layers that it cuts through to determine the order of the layers. So if you can remember this fact, that the intrusion and the fault are younger than the layers, it makes it a little easier to figure out which layer is the youngest layer and which layer is the oldest. So looking at this, we've got nice numbers for the layers, A, B, C, and D, okay? So let's think which one is the oldest one and which one is the youngest one, going from oldest to youngest, okay? So see the intrusion here and see the fault. Notice the fault. So I'm going to show you these two things before we get going. So there's the fault. There's that crack in the rock. Okay. So remember, that intrusion, if it cuts through a layer, is younger than that layer. If the fault cuts through a layer, it's younger than that layer. Okay. So we can use, remember, the law of superposition here to also figure out the rock layers too. Because remember, superposition is if it's lower than layers above it, it's older. Okay. So the oldest layer in this example here is definitely what? What are you thinking? It's A, right? So A is the oldest. The law of superposition tells us that. Okay. The next oldest, well, let's think here. Is it B? B is a little bit above that. That would make sense. It is B. Okay, so B is the next oldest because if you take a look, it is on top of A. Okay, the next oldest is C. Okay, but then you start to see that intrusion cut through. So the intrusion cuts through a little bit of A, cuts through B, so it's younger than B, cuts through C, so it's younger than C, but it doesn't cut through D. So D's got to be younger than it, right? Okay, so the intrusion would go next in terms of oldest. Then layer D, then the fault, because the fault, I'll see right there, see the fault cuts through all the layers, including D. Remember, if the fault cuts through a layer, it's younger than that layer. So since the fault cuts through layer D, which is the top layer, the fault is the youngest thing, or the most recent thing that has occurred. So to go backwards with this, the most recent occurrence is the fault, then layer D was made, okay? Then this magma bubbled up here, right? Then going back into history, then layer C was made, then B, then A, the longest ago, okay? So we're going to use this rule, the law of cross-cutting relationships, along with the law of superposition, and everything else we talked today, to do some practice and really nail down how a scientist compare different rock layers to figure out which are older, which are younger, and whatnot. Okay, so hope you enjoyed this. It wasn't too painful. Maybe not the most exciting topic to talk about, but pretty important, right? Because it really gets us to think about just how scientists go about their work and kind of use logic, sort of just understanding with only simple observation of sight, you can really figure out some pretty important stuff in terms of which rocks are older than others. Okay, so hope you have a good afternoon or evening or night or morning or what time of day you're watching this. And yeah, that's all. Go Bills. Thanks.